Hello, and welcome to the Sleepy Curiosity channel. As you find a comfortable position, let your body begin to release the weight of the day. If this gentle journey is already starting to slow your thoughts, consider subscribing now, so these stories can keep finding you night after night. Now, let the relaxation settle into your breathing. The human mind has been able to build cities, compose symphonies, solve impossible equations, and still can't explain, with complete precision, what happens inside itself. That's not scientific modesty. It's one of the most open problems science has ever known. There's something fascinating about a discipline that studies the instrument with the instrument itself, like an eye trying to see itself. And the more we look, the more surprising it becomes. Psychology has existed as a formal science for just over 150 years. But the questions it tries to answer have existed for millennia. What motivates us? Why do we behave in ways that sometimes contradict our own values? Why do we remember some things and forget others so completely that it's as if they never happened? For centuries, those questions belonged to philosophy and religion. It wasn't until 1879, when the German scientist Wilhelm Wundt created the first laboratory dedicated to the scientific study of the mind, in the city of Leipzig, that psychology began to be treated as an experimental discipline, with methods, measurements, and testable hypotheses. What Wundt was doing in that laboratory seemed simple enough. He asked people to describe, as precisely as possible, what they felt when perceiving external stimuli. This method, known as systematic introspection, had obvious limitations. But it marked an important break. The human mind was no longer just a subject of speculation, it became an object of investigation. And there's a detail that changes everything about this starting point. By making the mind something that could be investigated, Wundt opened a door that, once opened, could never be closed again. What seemed simple wasn't. There's a distinction that seems obvious, but still generates debate among scientists. The brain and the mind are not the same thing. The brain is a physical organ, about 3 pounds of nervous tissue. The mind, on the other hand, is the set of processes that emerge from that organ: thoughts, emotions, perceptions, memories. No neuroscientist has found, to this day, the location of the mind in the brain. There's no specific region where consciousness resides. What exists are distributed networks of neurons that, when activated in specific patterns, produce subjective experiences: the sensation of seeing a color, of feeling longing, of making a decision. This separation between the physical and the experimental is known as the hard problem of consciousness. Explaining how biochemical processes produce subjective experiences remains one of the most open problems in science. And what makes it even more intriguing is that everyone knows what it's like to have a subjective experience, but no one can fully explain why it exists. In the early 20th century, psychology split into currents with radically different views on what it should study. On one side, Sigmund Freud argued that most of human behavior was driven by unconscious forces, repressed desires, internal conflicts, childhood experiences that conscious memory couldn't reach. On the other side, John Watson argued that psychology should completely ignore anything that couldn't be observed and measured. For Watson, talking about the mind or the unconscious was pseudoscience. What mattered was behavior, stimuli, responses, conditioning. This current became known as behaviorism. These two views shaped decades of research and clinical practice. And although neither one won out, each revealed real aspects of how humans function. The tension between them was, in a way, productive. It pushed psychology to refine its methods and broaden its questions. And this is where things get strange. Sometimes the greatest advances in science don't come from answers, but from conflicts that last decades. One of the most counterintuitive discoveries of modern psychology is that a large part of our behavior isn't the result of conscious decisions. Studies in cognitive neuroscience suggest that the brain begins preparing an action before the person is even aware they're going to act. The most cited experiment in this context was conducted by neuroscientist Benjamin Libet in the 80s. He asked participants to move their wrist whenever they wanted, while monitoring brain activity. The result was surprising. The neural activity associated with the movement began roughly 550 milliseconds before the person reported having decided to move. This doesn't mean that free will doesn't exist. The interpretation of that experiment is still debated with intensity. But it suggests that consciousness may be, in part, a narrative the brain constructs after the processes have already been set in motion. A story we tell ourselves about choices that may have already been made. What almost no one realizes is that this idea has profound implications for how we understand responsibility, identity, and the very notion of being the author of a life. And those implications become even more complex when we start to understand how the brain perceives the world. There's something curious about the way we perceive the world. We never perceive reality directly. What we call seeing, hearing, or feeling is actually an active construction of the brain, an interpretation based on incomplete sensory data, prior expectations, and context. A simple example illustrates this. When you read a sentence with a misspelled word, you often don't notice the mistake. The brain automatically corrects it based on what it expects to find. The same happens with visual illusions. The brain fills in information that the eyes don't capture, using shortcuts that work in most situations, but fail in specific cases. This process is called top-down perception, the influence of what we already know on what we think we're seeing. And it's constant, invisible, and surprisingly powerful. In practical terms, it means that two people can observe the exact same event and have genuinely different perceptual experiences. Not because one of them is wrong, but because both brains are constructing slightly different versions of the same reality. And there's a detail that changes everything here. If what we perceive is a construction of the brain, then the world we experience is not the world itself, it's the model our nervous system builds second by second, with extraordinary efficiency and specific failures that only show up under particular conditions. The idea that we have 5 senses is a simplification that science left behind quite some time ago. Beyond vision, hearing, touch, smell, and taste, humans possess other functional sensory systems, among them proprioception, which is the perception of the body's own position in space, and interoception, which is the perception of the organism's internal states, such as heartbeat, hunger, and body temperature. Interoception has been getting special attention in recent research because it appears to be intimately connected to emotions. Part of what we call feeling an emotion may actually be the brain's interpretation of internal body signals, an accelerating heart rate, muscle tension, changes in breathing. This means the body isn't just a vehicle the mind uses. It's an active source of information that influences how we think, decide, and feel. The boundary between mind and body, in that sense, is much less clear than we tend to imagine. And this discovery, seemingly technical, profoundly changes what it means to take care of the mind. For a long time, it was believed that the adult brain was essentially fixed, that after a certain age, neural connections were established and significant structural changes were impossible. That view has been revised quite definitively over the last few decades. The concept of neuroplasticity describes the brain's ability to reorganize its connections in response to experience, learning, and even injury. Studies with musicians, for example, show that the motor and auditory cortex expands and reorganizes with years of practice. Studies with London taxi drivers, who need to memorize extraordinarily complex maps, showed an increase in the volume of the hippocampus, a region associated with spatial navigation. What this implies is significant. The brain you have today is, in part, the accumulated result of the experiences you've lived. And it continues to be shaped, to some degree, throughout your entire life. The intensity of plasticity decreases with age, but it never reaches zero. What we do, what we learn, where we place our attention, all of it leaves physical marks on brain tissue. This starts to get more interesting when we realize that plasticity isn't just positive. The brain reorganizes in response to any repeated experience, not only the ones we consciously choose. Habits, learned fears, patterns of response to stress, all of these are expressions of plasticity operating in every direction. There's a phenomenon called the blind spot that illustrates well how perception is, in practice, a functional illusion. Each human eye has a small region on the retina where the optic nerve connects to the brain, and that region has no photoreceptors. This means there's literally a part of your visual field that you can't see. The curious thing is that you never notice that gap. The brain automatically fills it in using information from the surrounding area and from the other eye. creating a continuous and coherent image. This filling in is so efficient that it takes a specific test to reveal the blind spot. This raises a broader question. If the brain fills in gaps in vision without us noticing, in what other areas is it doing the same thing? The answer, according to research in cognitive psychology, is that this kind of filling in and interpolation happens constantly, in memory, in social perception, in moral judgment. What seems simple, isn't. Psychology went through a significant crisis in the last decade, known as the replication crisis. Classic and widely cited studies, some of them used in textbooks for decades, couldn't be reproduced when other researchers tried to repeat them with greater methodological rigor. A coordinated project in 2015 attempted to replicate 100 studies published in psychology journals. Only about 36% produced results consistent with the originals. This doesn't mean psychology is pseudoscience, it means that part of the accumulated knowledge was built on small samples, fragile methodologies, and a publication bias that favored positive results. The crisis, paradoxically, strengthened the discipline. It accelerated the adoption of more rigorous practices, such as pre-registration of hypotheses and sharing of raw data. The psychology that emerges from this process is more cautious, more transparent, and probably more reliable. There's something beautiful in that idea, a science that grows stronger by honestly confronting its own mistakes. What almost no one realizes is that this process of self-criticism is, in itself, a piece of data about how the human mind works. We're just as subject to biases in our investigations as we are in our everyday perceptions. And that's precisely why the scientific method needs structures that protect us from ourselves. There's a question that seems simple until you try to answer it precisely. What exactly is the color red? The light that reaches your eyes has no color, it has a wavelength. Color is an experience the brain creates from that physical data. This means color exists in your mind, not in the world. This principle applies to practically everything we perceive. Sound doesn't exist in the air vibrates at frequencies, and the brain transforms those vibrations into sound. Heat, pain, taste, all of these are neural constructions based on physical signals. What we call reality is, in technical terms, an internal model generated by the brain. The implication of this isn't that the external world doesn't exist, but that our access to it is always mediated, always interpreted. Two different nervous systems can generate different subjective experiences from the same physical stimulus, and both can be right within their own perceptual frameworks. This isn't an abstract philosophical idea. It's concrete neuroscience. The human brain processes an enormous amount of sensory information every second. Estimates suggest something around 11 million bits per second arriving through the sense organs. Consciousness, however, processes only a tiny fraction of that, about 40 to 50 bits per second. This means there's a massive and constant filtering happening below the level of consciousness. The brain decides, largely automatically, what deserves conscious attention and what can be ignored or processed in the background. This process is guided by factors like novelty, emotional relevance, and previously formed expectations. One direct consequence of this is the phenomenon known as inattentional blindness. In classic experiments, people focused on a visual task failed to notice completely obvious elements in their field of vision, like a person in a gorilla suit walking through the middle of a scene. The brain didn't register what it wasn't looking for, even when the stimulus was literally right in front of their eyes. And there's a detail that changes everything here. If the brain filters so aggressively what enters consciousness, then conscious experience isn't a faithful representation of the world, it's an editorial selection. A curated version of reality, assembled according to criteria we rarely examine. Most people imagine memory as something like a filing system. You store an experience, it stays saved, and when you need it, you retrieve it intact. That analogy is intuitive, but it's wrong in fundamental ways. Human memory doesn't store fixed records. It reconstructs. Every time you remember something, the brain doesn't simply open an existing file. It reactivates patterns of neural activity distributed across different regions, and assembles the memory at the moment of retrieval, using stored fragments, but also filling in gaps with information from the current context, from expectations, and from knowledge acquired after the original event. This has a direct consequence. Remembering something is also, to some degree, changing it. The act of retrieving a memory temporarily destabilizes it, a process called reconsolidation, and it can be altered before being stored again. With each recollection, the memory may drift subtly from the original version. The past, in that sense, isn't fixed. It moves a little every time we look at it. One of the most unsettling discoveries of cognitive psychology is that false memories aren't rare, aren't exclusive to people with memory problems, and can be extraordinarily vivid and detailed. Anyone with a perfectly healthy memory can remember with conviction something that never happened. Researcher Elizabeth Loftus spent decades studying this phenomenon. In a classic experiment, she managed to implant in adults the memory of having gotten lost in a shopping mall as a child, a completely fictional event. About a quarter of the participants not only accepted the suggestion, but went on to elaborate details about the invented event, complete with emotions and specific contexts. The mechanism behind this is the same one that makes memory flexible and useful. The brain doesn't perfectly distinguish between what was lived, what was imagined, and what was suggested. Information introduced after the event, through leading questions, conversations, or simply the passage of time, can integrate into the original memory without leaving any visible trace. This shouldn't happen, but it does. The case that contributed most to our understanding of memory was that of Henry Molaison, known in the scientific literature for decades simply as HM. In 1953, Molaison had parts of his hippocampus surgically removed to treat severe epilepsy. The procedure worked for the epilepsy, but produced a devastating effect. He completely lost the ability to form new long-term memories. Molaison could hold a conversation, reason, learn new motor skills. His short-term memory functioned normally. But every new conversation, every new face, every new event disappeared within minutes. He died in 2008 without having been able to form a lasting memory since the age of 27. His case taught us more about memory than decades of experiments with uninjured subjects. A life that became, paradoxically, one of the greatest gifts neuroscience has ever received. There's an effect called spacing that is one of the most robust findings in all of learning psychology, and also one of the most ignored in actual educational practice. Studying the same material in sessions distributed over time produces far superior retention compared to studying the same material in a single long session right before an assessment. The paradox is that spacing feels less efficient during studying. The material seems harder to retrieve, which creates a sense of slower progress. But it's precisely that difficulty of retrieval that strengthens long-term memory. The feeling of ease during intensive studying doesn't correspond to the actual retention that follows. This starts to get more interesting when we realize that the brain seems to learn not just through repetition, but through controlled difficulty. The effort of retrieving something that was starting to be forgotten, and succeeding, seems to be one of the most powerful signals the memory system uses to decide what's worth keeping. Emotional memory follows different rules than factual memory. Events with a strong emotional charge, especially those involving fear, danger, or intense surprise, are consolidated in a more robust and lasting way than neutral events. This involves the amygdala, a brain structure that functions as a modulator of the intensity with which memories are recorded. The mechanism has clear evolutionary logic. Remembering with precision situations that were dangerous or emotionally significant increases the likelihood of survival. The problem is that this system doesn't distinguish well between real threats and perceived threats, and can consolidate intensely negative memories of events that, objectively, posed no risk to life. It's precisely this mechanism that underlies post-traumatic stress disorder. Trauma can be understood, in part, as an emotional memory that was consolidated with excessive strength and that resists the normal processes of extinction and contextualization. The event was recorded with an intensity that the regulatory system can't adequately modulate. What almost no one realizes is how much memory shapes not only the past we remember, but the future we imagine. Research shows that the hippocampus, the central structure for forming new memories, is also fundamental for simulating future events. People with damage to the hippocampus don't just lose past memories, they lose the ability to imagine future scenarios with richness and detail. For a long time, emotions were treated as the opposite of reason, irrational forces that interfered with clear thinking and sensible decisions. This view, which goes back to the Greek philosophers and ran through centuries of Western thought, was substantially revised by neuroscience in the last few decades. Neuroscientist Antonio Damasio studied patients with damage to brain regions linked to emotional processing. These patients kept their capacities for logical reasoning, language, and factual memory fully intact. But they became unable to make simple practical decisions in everyday life: what to eat, who to meet with, how to organize their time. Damasio's conclusion is that emotions function as guiding signals for the decision-making system. They assign value to options and scenarios based on past experiences, speeding up and directing the process of choice. Without that emotional component, pure reasoning becomes slow, disoriented, and functionally paralyzing. Reason, it turned out, needs emotion to work. One of the most influential theories about the nature of emotions proposes something that initially seems counterintuitive: emotions aren't automatic reactions that simply happen to you, they're active constructions of the brain, generated from raw bodily states combined with culturally learned concepts. This perspective, developed by neuroscientist Lisa Feldman Barrett, argues that what we call fear or anger aren't natural categories with fixed neural signatures. They're interpretations the brain makes of states of bodily activation, accelerated heart rate, muscle tension, hormonal changes, using the conceptual repertoire it has learned over a lifetime. One practical implication of this is that expanding emotional vocabulary, the ability to distinguish and name emotional states with precision, isn't just a linguistic skill. It's a way of increasing the resolution with which the brain processes and regulates emotions. People with a richer emotional vocabulary tend to regulate emotions more efficiently. The words we have for what we feel shape how we feel. The body doesn't just express emotions, it generates them. Studies using botulinum toxin provided interesting evidence in this direction. When people with Botox injections in the area between their eyebrows read emotionally charged texts, they reported lower emotional intensity and showed reduced neural activity in regions linked to emotional processing. This doesn't mean that emotion is purely physical. The process is bidirectional and involves the brain and body in continuous feedback loops. But it suggests that bodily expression isn't just a passive reflection of an internal emotional state, it actively participates in constructing that state. What we do with our face, our posture, our breathing doesn't just express what we feel. It shapes what we feel. And there's a detail that changes everything when we think about emotional regulation, expressive suppression. Trying not to show what you're feeling doesn't reduce the internal experience of the emotion. In fact, it increases physiological activation and demands considerable cognitive resources. The emotion doesn't disappear when it's hidden. It just changes address. There's a phenomenon called emotional contagion that operates constantly and largely automatically in human interactions. When you're with someone who is happy, anxious, or irritated, you tend to unconsciously synchronize your facial expressions, posture, and tone of voice with theirs, and that bodily synchronization produces, to varying degrees, the corresponding emotional state in you. Emotional contagion has implications that go beyond individual interactions. Studies on social networks showed that emotional states spread through relationship networks, not just through direct communication, but through cascade effects in which one person's mood influences that of their contacts. The emotional environment of a group isn't just the sum of individual states, it's an emergent phenomenon with its own dynamics. One of the most replicated findings about happiness directly contradicts some of the most common intuitions about what will make us feel good. People consistently overestimate both the intensity and the duration of the emotional impact of future events, positive and negative. You probably won't be as happy for as long as you imagine if you win the lottery. And you probably won't be as devastated for as long as you fear if you lose a job or a relationship. The mechanism behind this faster-than-expected recovery is called the psychological immune system, a set of cognitive processes that people use to find meaning, reassess situations, and adjust expectations after negative events. This system operates largely outside of consciousness and is more efficient than people anticipate when making predictions about the future. This starts to get more interesting when we realize that this same capacity for adaptation, so useful after losses, also means that material achievements tend to satisfy us for less time than we predict. The psychological immune system protects us from losses and, at the same time, shortens our pleasures. It's designed for balance, not for permanent euphoria. Human beings aren't rational agents who occasionally make mistakes, they're agents with systematic and predictable biases that deviate from rationality in consistent and measurable ways. This insight, developed by psychologists Daniel Kahneman and Amos Tversky starting in the 70s, changed not just psychology, but economics, medicine, and public policy. The best-known framework from this work distinguishes two systems of mental processing. The first is fast, automatic, associative, and emotionally charged. It operates without conscious effort and is responsible for most everyday decisions. The second is slow, deliberate, logical, and requires effort. It's activated when new or complex situations demand careful analysis. The problem isn't that the fast system exists, it's efficient and functionally necessary. The problem is that it frequently takes over in situations that would call for more careful analysis, and the slow system rarely questions its conclusions. Most of the documented cognitive biases can be understood as byproducts of the fast system operating outside its domain of competence. The anchoring bias is one of the simplest to demonstrate and one of the hardest to avoid. When a person is exposed to any number before making a numerical estimate, even if that number is clearly arbitrary and unrelated to what's being estimated, it exerts a significant influence on the final answer. In a classic experiment, participants spun a rigged wheel that always landed on 10 or 65. They were then asked about the percentage of African countries in the UN. Those who had seen the number 65 gave systematically higher estimates than those who had seen the number 10, even though they knew the wheel had no relation whatsoever to the question. A meaningless number, changing an estimate about the real world. There's a fundamental asymmetry in the way people evaluate gains and losses. Prospect theory demonstrated that the psychological pain of losing something is roughly twice as intense as the pleasure of gaining the same amount. Losing $100 hurts psychologically about twice as much as gaining $100 feels good. This asymmetry, called loss aversion, explains a range of seemingly irrational behaviors, why people hold on to losing investments for too long hoping for a recovery, why they're more motivated to avoid punishments than to pursue equivalent rewards, why they resist change even when the change promises gains. In ancestral environments, where losses could be fatal, being more sensitive to losses than to gains had adaptive value. In modern financial markets, that same mechanism frequently works against a person's own interests. The framing effect demonstrates that the way information is presented, and not just its content, profoundly influences decisions. In a classic experiment, participants evaluated a public health program described in two different ways. In the first version, the program would save 200 of the 600 people affected. In the second, 400 of the 600 people would die. The two descriptions are mathematically identical. But the first, framed in terms of gain, was consistently preferred. Framing works because the fast processing system responds to the emotional flavor of the information before the slow system has a chance to verify the logical equivalence. The same reality, described in different ways, produces different choices. The confirmation bias is probably the most studied and the most broadly relevant of all cognitive biases. It describes the tendency to seek, interpret, and remember information in ways that confirm already existing beliefs, and to ignore or minimize information that contradicts them. The most unsettling implication is that confirmation bias isn't mitigated by greater intelligence or education. In some studies, people with higher analytical reasoning ability are more skilled at constructing justifications for pre-existing beliefs. Critical thinking can, paradoxically, be used in service of confirmation rather than correction. The mind isn't just an instrument for seeking truth. It's also an instrument for defending what it already believes. The architecture of choice, the design of the context in which decisions are made, has an influence on behavior that rivals, and frequently surpasses, the influence of information and education. Small changes in the way options are organized can dramatically alter which ones get chosen. The most cited example comes from retirement savings programs. In companies where employees need to actively opt in to participate in the plan, enrollment rates are typically low. In companies where participation is the default option and employees need to actively opt out, enrollment rates reach 90%, with the same employees, the same plans, and the same financial incentives. All that changed was the default. And the default changed everything. The brain's reward system, centered on the dopaminergic circuit, doesn't work the way most people imagine. Dopamine isn't the neurotransmitter of pleasure, it's more precisely the neurotransmitter of anticipation, seeking, and reinforcement learning. Dopamine fires strongly not when the reward arrives, but when it's anticipated, and even more strongly when it's uncertain. Predictable rewards generate less dopamine than intermittent rewards. This is the neural mechanism behind the compulsiveness of gambling, social media with unpredictable notifications, and many seeking behaviors that seem hard to voluntarily stop. The system isn't broken in people who develop compulsive behaviors, it's working exactly as it was evolutionarily designed to, in a context where uncertainty and reward were central elements of survival. The problem is that modern environments exploit this system with a precision that ancestral environments could never have produced. Ivan Pavlov was studying the digestive system of dogs when he made an observation that would change the course of psychology. He noticed that the dogs began to salivate not only when they received food, but when they saw the assistant who normally brought it, before any food had appeared at all. The animal had learned to associate a neutral stimulus with a response that originally only occurred in the presence of the biologically relevant stimulus. What Pavlov discovered wasn't just a trick with dogs, it was a fundamental mechanism of learning that operates in virtually every organism with a nervous system. Phobias, emotional responses to specific songs, food preferences developed after nausea, anticipatory anxiety in contexts associated with negative experiences, all of these are expressions of the same basic mechanism of learning by association. Albert Bandura demonstrated in the 60s something that the dominant behaviorism of the time had difficulty accommodating. People learn by observing other people, without needing to perform the behavior or receive direct reinforcement. This mechanism, observational learning, showed that learning is a cognitive process, not just a chain of stimuli and responses. Observational learning has far-reaching implications for how we think about the influence of media, parental models, peers, and reference figures. People don't just imitate behaviors, they absorb patterns of how to act, what to value, and which behaviors are socially acceptable through the continuous observation of others throughout their entire lives. The attachment theory proposes that human beings have a fundamental biological need to form close emotional bonds with caregivers, and that the quality of those bonds in the first years of life has lasting consequences for emotional and social development. The attachment style formed in childhood doesn't determine a person's emotional destiny, but it creates internal patterns of how relationships work, how reliable other people are, and how worthy of care the self is. These patterns tend to replicate in later relationships, unless they're actively modified by new experiences or by therapeutic processes. What we learned about relationships when we were too young to learn anything, learns right alongside everything else. The adolescent brain is in a phase of intense remodeling, and two critical parts of this system develop at different speeds. The limbic system matures relatively early, with acceleration at puberty. The prefrontal cortex, responsible for impulse control, long-term planning, and evaluation of consequences, only reaches full maturity around the age of 25. This gap creates a period in which the acceleration system is fully operational, but the braking system is still under construction. This doesn't mean that adolescents are incapable of good decisions. In low emotional pressure contexts, they often decide just as well as adults. But in contexts of high emotional arousal and visible immediate rewards, the balance between impulsivity and control tilts differently. Research on psychological aging has produced a surprising result called the well-being paradox. Older people consistently report higher levels of emotional satisfaction and subjective well-being than younger adults, despite facing more losses. Part of the explanation seems to involve a shift in the way time is perceived. As people perceive the time horizon as more limited, they prioritize emotionally meaningful relationships and experiences over goals of expansion and acquisition. This reorganization of priorities appears to be associated with a richer emotional life and greater satisfaction, a form of adaptive wisdom that emerges with aging. Genes and environment aren't independent forces that simply add up, they interact in complex and bidirectional ways. Genes influence which environments a person seeks and how they respond to them. The environment influences which genes are expressed and when. Childhood trauma can leave epigenetic marks that affect the functioning of stress systems for decades. Personality is one of the most commonly used concepts in everyday life and one of the most contested within psychology. The most widely accepted model today describes personality across 5 broad dimensions: openness to experience, conscientiousness, extroversion, agreeableness, and neuroticism. This model wasn't built from a theory, it emerged from statistical analyses of how traits naturally cluster in personality assessments across different cultures and languages. One of the most fascinating questions about personality is how much it changes over a lifetime. In general, conscientiousness and agreeableness tend to increase with age. People become more organized, more reliable, and more cooperative. Neuroticism tends to decrease. People become emotionally more stable. Personality isn't a fixed destiny, it's a system that keeps adjusting in response to what life presents. One of the most disturbing experiments in the history of social psychology was conducted by Stanley Milgram in 1961. Participants were instructed by an experimenter to administer increasingly powerful electric shocks to another person every time they answered a question incorrectly. The shocks were fictional, but the participants didn't know that. In the original experiment, about 65% of participants reached the maximum shock level, labeled dangerous, 450 volts, simply because an authority figure in a white lab coat kept saying, "Please continue." The result didn't reveal a special cruelty in these individuals. It revealed the extraordinary power of social context and perceived authority over human behavior. Social conformity, the tendency to adjust beliefs and behaviors to align with those of a group, was studied systematically by Solomon Asch in the 50s. When everyone around them gave a clearly wrong answer with conviction, about 75% of actual participants agreed with the wrong answer in at least one round. What participants reported afterward was revealing. Some genuinely began to doubt their own perception. Others knew they were wrong, but didn't want to seem different or foolish. Conformity operated both at the level of perception and at the level of expression, and both forms have equally important implications for how groups shape individual thinking. Social identity, the part of the self-concept that derives from belonging to groups, is far more powerful than was once assumed. What classic experiments showed in a striking way is that this process can be activated by completely trivial memberships. People divided into groups based on arbitrary criteria immediately began favoring members of their own group in resource distributions, even when doing so brought no personal benefit whatsoever. The implication is that in-group favoritism and discrimination against the outgroup don't require a history of conflict, real differences in interest, or significant distinguishing characteristics. Simple social categorization seems to be enough to activate patterns of favoritism. This makes the problem of prejudice and discrimination far more structurally rooted than models based solely on explicit hostility can capture. The relationship between language and thought is one of the oldest and most contested questions in cognitive psychology. There are clear forms of thinking that occur without language: spatial thinking, visual reasoning, musical intuitions. But language also influences thought in ways that go beyond simply expressing ideas that were already formed. Naming a category makes its members more cognitively salient. Having words for fine distinctions makes it easier to notice and remember those distinctions. Language doesn't create thought, but it shapes its texture, its speed, and its granularity in ways that are hard to undo. And this means that the language we speak isn't just a tool for communication, it's also a tool for perception. Sleep is often treated as a period of inactivity, the brain shutting down to rest. That view is profoundly incorrect. During sleep, the brain is extraordinarily active, carrying out processes of memory consolidation, emotional regulation, and metabolic cleanup that simply can't occur adequately during wakefulness. One of the most important discoveries about sleep in recent decades was the identification of the glymphatic system, a network of channels around the brain's blood vessels that expands during sleep and allows cerebrospinal fluid to flow through brain tissue, removing metabolic waste accumulated during neural activity. Among that waste are proteins associated with the development of neurodegenerative diseases. This means sleep isn't just useful for memory and mood, it's a maintenance necessity for the brain. Chronic sleep deprivation isn't just tiring, it's literally toxic at a neurological level, allowing the accumulation of metabolic byproducts that the nightly cleaning system can't adequately remove. Dreams are one of the most universal and most enigmatic phenomena of human experience, and science still hasn't reached a consensus on their function. One theory proposes that dreams evolved as a form of simulation of threatening situations, a safe environment to practice responses to danger. This would explain why dreams involving threats, pursuits, and dangerous situations are so universally common. Other theories emphasize the role of dreams in emotional integration, processing emotionally charged experiences from the day in a context where stress hormone levels are lower than during wakefulness. An opportunity to reprocess emotional memories without the chemical intensity of the original stress. A kind of nightly therapy that happens without us ever asking for it. Human motivation is often thought of in terms of external rewards, salaries, grades, recognition. But one of the most provocative findings in psychology is the overjustification effect, introducing external rewards for activities a person already does for intrinsic pleasure can reduce their interest in that activity. Children who drew for pleasure and began receiving rewards for it drew less when the rewards were removed than children who had never received rewards. The external reward had replaced the internal motivation, not reinforced it. What seems simple, isn't. And what seems like an incentive can, under certain conditions, work as the opposite. Depression is often popularly described as a lack of serotonin, a simplification that contemporary neuroscience considers inadequate. The serotonergic hypothesis of depression has been significantly revised. This doesn't mean that antidepressants don't work. Some of them work for some patients, although the exact mechanisms aren't completely understood. It means that depression is a far more heterogeneous phenomenon than the previous model suggested, with distinct subtypes, multiple biological mechanisms involved, and psychological, social, and situational contributions that interact in complex ways. Depression probably isn't a single disease with a single cause, it's a clinical category that groups conditions with similar phenomenologies but distinct mechanisms. The placebo effect is one of the most studied and least completely understood phenomena in medicine and psychology. It describes the real improvement, measurable physiologically, that occurs when a person receives an inert treatment believing it to be active. The placebo isn't imagination, it's real biology mediated by expectation and meaning. Studies have shown that placebos activate the same neurobiological systems as their corresponding active treatments. Placebos for pain activate the endogenous opioid system. Placebos for Parkinson's activate the release of dopamine in regions of the motor circuit. What this reveals is that expectation and the context of care have direct biological effects, not by magic, but because the brain uses expectations to prepare the organism for anticipated future states. Personal identity, the continuous sense of being the same person over time, is a psychological construction far more fragile and elaborate than everyday experience suggests. The brain actively generates a coherent narrative of the self, connecting memories, values, and experiences into a story that feels continuous and stable. But that narrative is constructed, and it can come undone. Research on the default mode network, the brain system most active during self-referential thinking, suggests that the narrative self is sustained by continuous and energetically costly neural activity. When this network is disrupted, by deep meditation, by psychedelics, or by certain injuries, the sense of self shifts in ways that reveal its constructed nature. The self that seems to be the stable observer of all experiences is, itself, a product of the brain activity it observes. One of the most active frontiers of contemporary psychology is the investigation of how social and structural factors, poverty, inequality, discrimination, isolation, affect mental health and cognitive functioning. Psychologist Sendhil Mullainathan and economist Eldar Shofar demonstrated that scarcity captures cognitive attention involuntarily, reducing the mental bandwidth available for other tasks. People in chronic poverty don't make worse decisions because they have less cognitive capacity. They make worse decisions because part of their cognitive capacity is constantly occupied with managing scarcity. This has profound implications for public policy, and for how we judge the choices of people living under conditions of disadvantage. Psychology arrived at the 21st century with a far more sophisticated, and far more humble, understanding than it had in the previous century. It learned that the mind is at once biological and social, individual and cultural, conscious and deeply unconscious. It learned that the tools it uses to measure human behavior influence what it finds. And it learned that many of its previous certainties needed to be revised. What emerges from this integration is a discipline that, in its best versions, doesn't try to reduce the human to simple mechanisms, but tries to map, with growing rigor and honesty, the extraordinary complexity of how we think, feel, relate, and build meaning. A task that, from what can be seen, is still far from finished, and that is, for that very reason, genuinely fascinating. And as you drift into a deep and restoring sleep, remember to subscribe, so these stories can keep finding you, night after night. Sleep well, and sweet dreams.